Welcome back to linear algebra. In this video, we're going to go through some of the other matrix operations. Calling this other matrix operations is a bit overstated. We've talked about several matrix operations previously, right? Elementary row operations. We've talked about adding matrices, scalar multiplication, and matrix multiplication. In this video, I'm going to introduce two other operations, the transpose and the power. There are two other major operations that are going to come a little bit later in the course. The inverse of a matrix and the determinant of a matrix. Each of those are fairly complex. There's a lot of theoretical underpinning to them, so they deserve their own video. But for this video, let's start off talking a little bit about powers of a matrix. If I get my head out of the way, if I let A be any n by n square matrix, I can define a power on matrix A as A raised to the k power, being A multiplied by itself k times. And since A is a square matrix, we know that the number of columns of this matrix is equal to the number of rows of this matrix. And the result will have the same number of columns as this matrix, which is still n, which is the number of rows of this matrix. And then the result will have the number of columns of this matrix, which is still n, which is the number of rows of that matrix, and so on all the way down the line. So the multiplication is defined in each step. And it's just a matter of working through multiplication over and over again. I don't feel like I need to go through a specific example showing you how powers work. We are going to compute them literally by performing a whole bunch of matrix multiplication, and matrix multiplication can be tedious and boring. Why do I keep writing a lowercase a? I don't know. All right, but two quick theorems here on properties of exponents. If I have a square matrix, n by n square matrix A, right, and we can implicitly understand that matrix A must be a square matrix because we put an exponent on it. Remember that exponents are only defined when we have a square matrix. So if I'm writing something that has an exponent, that thing I'm taking an exponent on must be a square matrix implicitly. I don't have to state that. That's something that you should be able to recognize fairly quickly as we jump into these. All right, but this is stated as a theorem, which means that we're going to have to prove it. And we don't have a lot of information. Really, all we have is the definition of uh, exponents on a matrix. We have some properties of matrix multiplication, and we have the fact that this is a square matrix, which doesn't have that much going for it anyway. But just using the definition of a matrix exponent, we can write that a to the m times a to the n is a multiplied by itself m times multiplied by a multiplied by itself n times. So all told, we have a being multiplied by itself m plus n times, which is exactly a to the m plus n. Likewise, the other rule, a to the m raised to the n, is a to the m times a to the m. N times. And what is a to the m? Oh, that's a multiplied by itself m times. And so we have a multiplied times itself m times, and then we have n of them. So we have m plus m plus m, n of them added together. And that's exactly what multiplication is for, right? M things added to itself n times is, by definition, m times n. Right? That's the definition of integer multiplication. And then, of course, that is a to the m times n power. And we have proven another thing. All right. So powers on matrices, kind of an interesting thing. We could go through and spend some time calculating it. But again, it's just a whole bunch of matrix multiplication. And instead of looking at that in general, I want to look at one particular case. And so let's introduce a little bit more vocabulary so that we can get into that. An upper triangular matrix is a square matrix where each entry below the main diagonal is 0. So remember that the main diagonal is this part of the matrix. And in an upper triangular matrix, the main diagonal can have non-zero entries. The part above the main diagonal can have non-zero entries, and everything down here is a 0. So there is a triangle formed where non-zero entries can occur, and that triangle is the upper part of the matrix, so we call it an upper triangular matrix. With that, you could probably write the definition of a lower triangular matrix without having to think about too much. It's practically the same definition. It is a square matrix where each entry above the main diagonal is 0. All right, so that's the thing to keep in mind with these naming conventions. Is that upper triangular and lower triangular is telling you where you can find things that are not zero. But the definition is all about where things are zero. You can have zeros on the main diagonal. You can have zeros below the main diagonal and still call it a lower triangular matrix. As long as nothing above the main diagonal is non-zero, then you have a lower triangular matrix. A diagonal matrix is both upper and lower triangular. That's the definition of a diagonal matrix, which is not a very obvious definition. But if we go back and think about what that says, well, every entry above the main diagonal is zero because it's lower triangular, and every entry below the main diagonal is zero because it's upper triangular. Right? A diagonal matrix is a matrix where every entry not on the main diagonal is zero. We've worked with one particular diagonal matrix quite a bit already. The identity matrix in any number of dimensions has ones, and here I guess I'm going to draw I5, has ones on the main diagonal and zeros everywhere else. That is definitely a diagonal matrix, and it's kind of a boring one for what we're going to be working on today, but it's one to keep in mind. When you're thinking about diagonal matrices, you're thinking about things that kind of generalize the identity matrix. And part of that means that some properties are going to be nice. The identity matrix we saw in a previous video was so useful because when you multiply by things, you get back the thing you multiply. In general, when you're doing multiplication with a diagonal matrix, some very nice things are going to happen, although not quite to that extent. One of those is what I want to look at in this video. Let's consider a diagonal matrix. I'll call it capital D. It has entries D1 through Dn on the main diagonal and zeros everywhere else. And with just that, I claim that if I want to take this diagonal matrix and calculate a power, d raised to the k power, I'm going to get a diagonal, d1 to the k, d2 to the k, all the way down dn to the k on the main diagonal, and zeros everywhere else. This doesn't work for most matrices. It does work for diagonal matrices. We really like having diagonal matrices when we're dealing with powers. Spoilers for the future, a large portion of the second half of the course is going to be looking at ways to take generalized matrices and turn them into diagonal matrices multiplied by something predictable as a way of figuring out the power of the other matrix a little bit more readily. But for now, we have a theorem, which means that we have to prove it. I'm not going to prove this in general, but I'm going to look at a couple of particular cases. So this is not a proof so much as a sketch of proof. Right, so I'm going to look at a 3 by 3 matrix. So D1, D2, D3, 0, 0, 0, 0, 0, 0. I'm going to square it. That means I'm going to take D1 and multiply it by itself. All right, well, the rules of multiplication. I want to dot row with column. So I'll get D1 times D1, 0 times 0, 0 times 0. Then I'll go row and column. I'll get D1 times 0, which is 0, 0 times D2, which is 0, 0 times 0, which is 0. And that's a pattern that's going to continue onward. So I get D1 squared, I get 0, I get 0. Second row, first column, I get a bunch of things multiplied times 0. Second row, second column, I'll end up with the D2 being multiplied by D2, giving me the D2 squared. And then I get a bunch of zeros until I go down to the third row, third column. And I apologize, I'm getting a little bit ahead of myself. What I want to do next is take the same diagonal matrix and cube it, which I can do by taking that matrix and multiplying it by the thing I just got by squaring it. And we can verify, right? Go through step by step, look at each of these, row by column. We'll get D1 cubed, we'll get 0, we'll get 0. We'll get 0, we'll get D2 cubed, we'll get 0, we'll get 0, we'll get 0, we'll get D3 cubed. All right, so we can see that this should work. And it will work. It will always work. All right, so again, it's not really a proof because I only looked at a couple of special cases, but it gives you the idea. And if we wanted to do this for an n-dimensional vector and doing it k times, we still could. Doing that would involve a proof by induction, which is an interesting proof technique. If anyone is currently taking discrete mathematics, you should be seeing that around about now or in the near future if you haven't already. But that's not something that we're going to be focusing on with this course. So I'm going to leave it at that. We can see that this is going to work. I could generalize this result and say that if I was multiplying two diagonal matrices together, the result would be a diagonal matrix whose entries on the main diagonal are the products of the corresponding entries of the two matrices, which is absolutely true, but not really anywhere useful. So I don't bother stating it, but it's an interesting result that we can at least talk about. Great. I'm going to come back to powers on matrices a little bit later on. But for right now, I'm going to change gears a little bit and look at the other operation that I promised for today. and that is the matrix transpose. Right. I talked about the matrix transpose when I am talking about powers because it starts to kind of look like a power. When we write a matrix transpose, we take our matrix and we put a superscript of a t on it. I've seen a couple of different notations for this. Typographically, usually we don't want the letter T. We want kind of something that looks more like the perpendicular line symbol, but upside down, which starts to look like a T because you probably were taught that the perpendicular line symbol was a T that was upside down. Um, you'll see in my printed notes and in the homework assignment what I mean by that. But as far as handwriting goes, I can't make them look different, so I'm not too worried about it. But the matrix transpose tells us to take a matrix given as Aij, and this could be any m by n matrix. And the transpose is going to be a matrix given by Aj, and that's going to be an n by m matrix. Right. Symbolically, that's kind of the powerful tool of thinking about it. But what we're really doing here, if you think about what those subscripts mean, we're taking the row index and we're turning it into the column. We're taking the column index and we're turning it into the row. We are swapping rows and columns. And that's not something that is immediately apparent when you start playing around with these. So even though the calculations are incredibly simple, I do want to go through a couple of examples to show you what I mean. All right, unlike the powers on matrix, a matrix transpose can occur on any size matrix. So consider here, we have a matrix with 4 rows, 3 columns, 2, 3, 4, 3, 7, 5, 4, 6, negative 1, 9, 8, negative 3. And I want to take the transpose. Well, the transpose swaps rows and columns. So we're going to go from a matrix that had 4 rows and 3 columns to a matrix that has 3 rows and 4 columns. The first column of the original matrix is going to be the first row of the new matrix. 2, 3, 4, 9. The second column of the original matrix is going to be the second row of the new matrix. 3, 7, 6, 8. And then third row or third column becomes the third row. 4, 5, negative 1, negative 3. Right. Once you start to see how this works, it makes a lot of sense. Talking about it in the abstract is not always immediately apparent what's happening. Since the transpose is a little bit different, that means it's going to take a little bit more to talk about the properties. The first three properties here, I think, are very quickly apparent. If you just think a little bit about what the transpose is doing, and you think a little bit about these operations, you should be able to convince yourself that A transpose is matrix A. If we're adding two matrices, A plus B transpose is A transpose plus B transpose. And for any constant K times A transpose, or K times A, the transpose of all of that, is the same thing as K times A transpose. And I apologize. I started writing down the header and then I got distracted because I was so excited about the thing to come. For any matrix A and B and for any scalar K, we have these properties. And then the fourth property here, if A times B is defined, then AB transpose is equal to B transpose times A transpose. That's the one that's a little bit weird. And there's a nice follow-up on that. If A is square, I can prove a property I'll call E. A to the K transpose is the same thing as A transpose to the K. All right, the only one of these I'm going to prove is property D. A, B, and C, I think, are pretty straightforward. I encourage you to take some time to think about them on your own. Property E follows pretty nicely from property D, but writing out the proof is a little bit messy and a little bit beyond what I want to get into this semester. D falls into the sweet spot where it's messy, but not so messy that I don't think that you can follow it, or I don't expect you should be able to follow it. And it lets us use some of the nifty tricks that we've used talking about matrix multiplication in a previous video. Right. When we're dealing with multiplication of matrices, for matrix A, we need to be able to talk about the row vectors. So I'm going to go ahead and name the row vectors that make up matrix A as little a1, little a2, down to little an. And then for matrix B, to define A times B, we need the column vectors. I don't need that to be that big. So we'll have B1 vector, we'll have B2 vector, and that'll go all the way down to Bn vector. Now, the definition of the matrix transpose swaps rows and columns. So A transpose, instead of being made up of these M row vectors, will instead be made up of the same M vectors written as column vectors. And likewise, the transpose of matrix B is going to be made up of the same n vectors, but instead of being column vectors, they are now row vectors. I always underestimate how tall A matrix has to be when I talk about the row vectors. Right? And what happens when we multiply these matrices together? If I multiply matrix A times matrix B, well, the definition is that each entry in the matrix is going to be the dot product of the corresponding row and column. So A1 dot B1, A1 dot B2, all the way down to A1 dot Bn. And we'll do that with the second row, and we'll do that with the third row, and we'll keep doing that until we get all the way down to AM dot B1, AM dot B2, all the way down to AM dot Bn. And then what happens when I want to multiply B transpose times A transpose? Right? Well, I'll get the first row of matrix B transpose, which is B1, and I'll dot that with the first column of A transpose, which is A1. I'll get B1 dot with A2, and I'll keep going until I get to B1 dot with AM. I'll do B2. I'll dot it with A1, A2, and all the way down till I get to AM. And I'll keep doing that until I get to the Bn, which I'll dot with A1 and A2, and all the way down to AM. But of course, we showed previously that the dot product is commutative. B1 dot A1 is the same thing as A1 dot B1. B1 dot AM is the same thing as AM dot B1. And look at what we have. On the main diagonal, these two matrices agree with each other. On the opposite extreme, we've flipped around. So we can see if we list out all of the entries that it must be the case that B transpose times A transpose is A times B, the whole thing transposed. Right? That proof, like I said, is a little bit messy. You have to really think about writing matrices as row vectors and column vectors. You have to think about all these dot products, keep everything straight in your notation, which is never fun, but hopefully possible, and that's good enough for us. So we have this surprising result. And again, if we just did the same thing over and over again for a square matrix, we would get the last result as well. But writing that out is kind of messy and not worth it. There is one last thing that I want to talk about in this video. It's again related to the symmetric, or related to the transpose, and it is called the symmetric matrix. And square matrix A is symmetric if and only if A is equal to A transpose. So for a matrix and its transpose to be equal, we're looking at a case where rows and columns match. So if first row, second column is a 2, then second row first column must also be a 2. If first row third column is -1, then third row first column must also be -1. And let's make this a 4 by 4 matrix so we don't have to write all that much. All right, second row, second column, we can put whatever we want, but then we have to start mirroring things. And we have to mirror things throughout the rest of the matrix. Right, so if you draw a line through the main diagonal and you think about trying to fold the matrix along that diagonal, you'll see that the entries of the matrix that line up are the same entry. That's what a symmetric matrix means. I've got a couple of theorems here. The first one is fairly simple. If A is symmetric, then raising it to the k power, it is still symmetric. All right, this is that last property of the transpose that I hadn't talked about. Right, AK transpose is the same thing as A transpose to the k power. But since A is symmetric, that means that A itself is equal to A transpose. And so I can replace the A transpose right here with just A. And so by definition here, we have that A to the K is also a symmetric matrix. I've got one more theorem on symmetric matrices. I'm not going to prove this one because it's something that you're going to be asked to prove in your assignment. Right. I want you to get a little bit of practice playing around with matrices before that one. So that's not the problem I'm going to assign for this video, but that is something that you should try on your own to prove that A times A transpose and A transpose times A are symmetric matrices. Not necessarily equal to each other, in fact, probably not equal to each other, but each on their own a symmetric matrix. Right? If matrix A is not square, then A times A transpose and A transpose times A are going to be two matrices of different dimensions. So it's definitely not symmetric with each other. They are two different matrices which are both symmetric. Now, what I want to do is look back at this result. For any square matrix A to the K transpose is the same thing as A transpose to the K. So let's take a look at a specific matrix A. One, 0, 2, 0, 2, 0, 1, 0, 3. All right. So it's not proving it in general, it's just showing in one specific case that it will work. But I'd like you to take this matrix, square it, and then take the transpose. And then take the same matrix, take its transpose, and then square it. All right, this is not a symmetric matrix, so the transpose is going to be something different. But I want you to go through that, verify for yourself that that property that I didn't prove is in fact real. See what you can do with that, and I'll see you in the next video.